Hello everyone. I trust you're all doing very well. Welcome to the test episode of our tutorials. Okay. Today we are going to solve a problem, and our main reference is the um, Thermodynamics and Engineering Approach by Eunice Angel and then Michael Boyles. Yeah. So today's problem is more or less like the manometer problem. Okay, we have a tank, okay, water in a tank which is pressurized by air, and the pressure is measured by a multi-fluid manometer as shown here. Now, when we say a multi-fluid manometer, we are looking at a manometer made up of what? More than one fluid. So here we have mercury, we have oil, and since we are using air here, sorry, with the water also goes in there, so it's more than one or two fluids within the manometer, right? So, and at 2 we have it exposed to what? Atmosphere. It's not connected to any tank, but here it's sealed. It's a closed tank, so the air pressure is what is exerting the pressure on the water interface, but here the manometer is open, so it's open to atmosphere. So on 2 it's atmospheric pressure that is acting on this. Oh, are we there? Good. So the pressure at 2 is the same thing as what? The atmospheric pressure. Now we are going to um, determine, let's see what the problem is saying, that we are to determine the gauge pressure of air in the tank if this information are given. So we have H1 is given, H2 is given, and then H3 is also given. Now we are to take the densities of water, oil, and then mercury to be this, that, and that respectively. Are you getting the idea? All right, so it's quite straightforward. Now, to solve this problem, we need to know what we are looking for. The goal is to find what? The gauge pressure, right, of the air. Now, the main assumption here is to assume that the pressure in the tank is uniform. Are you getting it? So the variation of it is with elevation here is negligible due to its low density. Okay, all right. So this means that we can easily determine the pressure, okay, at the air-water interface. Are you following? So if we are to go with that, this is how we're going to analyze this problem. Please take note that with these problems, manometer, we just walk through. It's the same approach. It's very, very easy and straightforward. Okay, so we are going to start from the tank and then walk through. It's like we are swimming through the fluid till we get out. We can also start from 2, jump in or hop in, swim through till we get out at the interface here. So we have to assume a sign convention so that people will know what we are doing. If we move down, we have it as what? Positive. If we move up, it's negative. Down, positive. Up, negative. Are you getting it? Now you notice that for the same fluid, we can see that if we move from here down and then here up at this interface here, this and that will cancel out. In a similar way, for the oil, if I consider this interface here and then the other interface, I'll show you, going up and coming down to this point, positive, negative, positive, they will cancel out. I'll only be left with this part here. There's no other fluid to cancel it out. But here in the mercury, if I move from this interface to this interface, they will cancel out. Positive, negative. I'll only be left with this height. Are you getting it? So that's why, if you've noticed, they didn't give you certain height. You have to just analyze and know why we are ignoring certain height. Are you getting the idea? Yeah, so it's, don't solve a problem and end up saying, excuse me, sir, we think this is an incomplete question because you didn't give a certain height. No, based on the analysis, you don't need all those heights. Okay, all right. So we are going to see how best we can solve this problem. Now, also note that we are going to use the pressure due to the weight of the fluid, right? So rho GH or gamma H. So what I mean is we are going to use this, that here. So we're following the idea that if I have P equals what? Rho GH. this is gamma. So I'm looking at rho is supposed to be the other way around. Sorry about that. So we have rho GH, which is easy, density times that, and this is the same thing as gamma H, where this the specific weight, right, which is rho G. I think they were given in the problem statement, right? Good. So we are going to solve this now. So we start from point 1, that's the interface. Then remember, let's take these sections out. We have common sections here. So this going up here and then coming down here, this is positive, this is negative. They will cancel out because I'm going to use from here. Then over here, to forget about the size of the tank, we are just focusing on the column. For water, I can see a common interface here where I have from here to this part here, and then going up from here, positive and negative, they also cancel out. Then, so meaning if I start from here and I'm moving, at this point I have to go up, right? Good. So that is what the trick we are going to use, okay? All right. So let's see. I'm going to start by saying that I'm starting from P1, okay? So P1, we are now going down from here to this interface because the remaining one here and that will cancel. So I'm just moving from here to there, which will give me, which fluid are we in? Rho of water. So, yes, so rho of water. So it will be plus rho of water GH1, because from this interface to that is H1. Then remember, if I continue down and that, they will cancel out. So I'm now on this interface, okay? If I go up and come down, they also cancel out. So I'm from here, I'm now here moving towards this height, this elevation. So meaning I'm going down, so I'm still in the positive direction. So plus, what fluid is that? Oil. So rho of oil G times what is the height there? Remember, from here to here is H2. So it will be H2. Then notice something. If I go down and then I come up, they will cancel out. Positive, negative. So I'm now on this interface. So I need to move from here to here. I'm going up, which is positive, and the fluid is mercury. So it will be, sorry, it's negative. It's negative because I'm going up. Positive in our case is coming down, so it's negative. So minus rho of mercury GH3. Now, because I'm at the interface 2, I'll just equate that to, let's say, P2. And this is the same thing as P atmospheric. Are you getting the idea? Good. Now, remember, this is gamma W, this is gamma oil, this is gamma mercury. So we are looking at P1 gamma, that's a specific weight of water, H1, plus specific weight of oil, H2, minus, specific weight of mercury, H3, and this is equal to P2 or PATM. Now take note that P, because we are looking for gauge, and by default, because this is also equal to 0, we can actually compute what? The P1 and say is the gauge pressure. In other words, I can say if I equate this to 0, I can say my P1 is basically the gauge. Or simply put, note that atmospheric absolute pressure equals what? P atmospheric plus what? P gauge, right? So if I say GAGE is also correct compared to the GUAGE, okay? So if I want P absolute minus PATM, I'll have what? PG, P gauge. So it's the same thing. So the P1 here is the absolute pressure in terms of PATM. So I can rewrite this as P1 equals, instead of the P2, I can say PATM, okay, minus gamma WH1 minus gamma, I'm taking everything across the equal sign, H2 plus gamma MH3. Are you getting the idea? So if I equate the P atmospheric to 0, I can easily compute my P1 as that. Or simply put, to show that we know what we are doing, we can say P1 minus PATM is simply what? P1 gauge, right? Which is simply equal to what? The remaining variables here, which is gamma MH3, okay, minus gamma WH1 minus gamma oil H2. So we now do the substitution. We put in all the values here and we get our solution. Are you following? So you can pause and get this note done, okay? And then we try to do the substitution, okay? All right. So by doing the substitution, let me clear this surface and then show you the analysis in details, okay? So all what I've explained, I've written them here too for you to understand them, okay? All right. So we start from that P1, we move down, plus water, that, then we go for this, right? So we ignore the other stuff there, plus this, then minus the mercury, that, and then we'll go to equate it to P2, which is the same thing as the P atmospheric. Now I'm showing that this section here will cancel this, okay? And then likewise, that will also cancel this. So similar, in a similar way, we have that. So that's why we ignore them. Now we know our data to be this, right? So we can easily compute these things. In the case where we are not given the specific weight and we have the the densities, we can just go ahead and work with them, okay? So in some books, they will just give you the specific weight, the gamma. You need to know how to play with them. All right. So simply put, we can substitute for this and then do this analysis. Or, like I said, we can say P1 minus PATM. We do this, okay? And then we equate it to P1 gauge. All right. So if we do the substitution, we are going to have this, and then the final answer will be 48.9 kilopascal. I need you to follow the steps and understand what we are doing, okay? All right. So that is basically for what we have, okay, for today's episode. Thank you for your time again. If you have any question, leave them in the comment section for me. I'll be grateful to answer them. All right. Thanks. Have a good one.